Hi class, welcome to the next video in the series. This is chapter 13.10. Today we're going to discuss the Taylor series. Taylor series is a power series. Let us have a function that we'll call f of x um, that we can represent as a power series. Then f of x is c naught plus c1 times x minus 1 plus c2 x minus a squared, so forth and so forth and so forth. Okay, where the distance between an x value and a is less than our radius of convergence. Okay. So note that if we plug in a to this power series about a, everything cancels except for the c naught. Okay. If I take the first derivative, I'm going to get c1, 2c2 x minus a, 3c3 x minus a squared. We saw this in the last video. Where again, I am convergent uh, as long as I'm within the radius of convergence. And if I plug in a into the first derivative, all of the terms fall out except for c1. If I take the second derivative, I'm going to get 2 times 3 times 4, and the powers are going to be as such, right? So if I just take this previous result that we had, take its derivative, but without actually multiplying everything in, right? So again, that 2c2 is here. This 2 comes down times 3c3, right? And then this is the next unseen term that we don't have. Okay, again, I would be convergent within a radius of r. And if I plug in a to the second derivative, I'm going to get out to c2. Right? If I take the third derivative, this is what the third derivative looks like. This 2, 3c3 is what's left. This is going to turn to 2, 3, 4, c4. The next term that we can't see here would be 3, 4, 5, C5. So you can see that there is a pattern forming here, right? If, again, within the radius convergence, if I plug in A, I'm going to have just this 2, 3, C3 term, okay? So following this pattern, if I look at all the derivatives, the nth derivative at A is going to have the form n factorial Cn. Right here, this is 3. We have 3 times 2 times 1. This is the second derivative, 2 times 1. The first derivative, just times 1, right? And then times the nth coefficient here. So if I solve for Cn, which would be nice if I had a formula for all of these coefficients here in a power series, I get the nth derivative of f evaluated at a, right? So not times a, just as a being plugged in, divided by n factorial. Okay. So now we have a formula for all of the coefficients of a power series. So putting this all together now, we can form our next theorem. If we have a function f that has a power series representation expansion at a, so that's basically just saying we can represent our function like this of some form, okay, that has this form. F of x is the sum starting from 0 to infinity, some set of coefficients times x minus a, since we're centered at a, uh, being convergent within a radius of r. Then its coefficients are given by the formula. C, the nth coefficient, is the nth derivative of f evaluated at a, that point that we are um, uh, about on our expansion, divided by n factorial, right? So therefore, f of x is equal to this series, right? So instead of writing the coefficients, I now write, just replace it with my formula for the coefficients. So before we had 1 divided by 1 minus x, and then we just kind of played around with that. We found different series for different functions by trying to get it to look like that. So in this section, we can find a power series for any function, right, by following this formula now. So it's helped us in order to find the formula much easier. So this series would look like f of a plus f prime over 1 factorial x minus a, right? Because the zero term would have this turn into just 1. So this is at 1. At 2, I'll have f double prime at a over 2 factorial x minus a squared. The next term is f, the third derivative at a over 3 factorial x minus a cubed plus and so forth continuously. Okay. We call this the Taylor series of our function f at a, okay, at the point a. So when a is equal to 0, it's really, really nice. This just looks like x to the n. Okay. So it's a special series because, again, normally we're interested in what happens around 0. So we will call that the Maclaurin series, okay, after another mathematician. So this has the form f of x equals the same formula, except we're evaluating at 0. And here it's just x to the n, right? The a, x minus 0 is just x, so it's x to the n. So that form will be f of 0, f prime of 0 over 1, just x, f double prime at 0, 2 factorial. This turns into x squared, right? The third derivative at 0 over 3 factorial. This would be x cubed, and so forth, and so forth. Okay, so let's look at an example. So let's find the Maclaurin series for f of x equals e to the x. So um, we need a few derivatives that we're going to evaluate at x equals 0. So remember, the Maclaurin series means that we are centered at 0, right? So we're going to need some derivatives evaluated at 0. And then once we have that, it's pretty straightforward for us to find our coefficients. Okay. Let's see. So we need to have enough that we can determine a pattern and hopefully write a summation formula. Sometimes we can't, sometimes it's too difficult to do that, and we just write out the first few terms. But whenever possible, we want to try to write out the summation form for our series, for our function, I should say. Note that for e to the x, it's nice because the function is equal to its derivative. That's the reason why e to the x pops up as a solution so often in differential equations. Because remember, a lot of times we need the derivative to be a constant multiple of our function, right? Y prime equals k times y. That was something that came up quite often. We're talking about things like populations and growth and money and stuff like that, right? So e to the x is a very special function. Um, so when I plug in 0 to my function, that's the same thing as plugging in 0 to my derivative. So that's very, very nice. And that's true for all the derivatives since it's always the same function. Okay, so e to the 0 is just 1. So this is a nice function to look at for an introduction into series representations, right? So for our Maclaurin series, our first term is going to be C naught, right? And so what is C naught? C naught is f of 0, right? There you go. Okay. F of 0, e to the 0 is just 1. Our next term is going to be the first derivative at 0, which is 1, um, over 1 factorial, which is 1 times x to the first power, so that's just x. Next, we'll have 1 over 2 factorial, x squared, so 1 half x squared. Then 1 over 3 factorial, x cubed, okay? 1 over 4 factorial, x to the fourth, and so forth, and so forth. So our sum can be written as a sum. There should probably be equal sign here. Change that in the reader. But the series can be represented as the sum from 0 to infinity of 1 over n factorial, x to the n power. Okay. If we look at the convergence of this, again, remember, ratio test, everything is plus 1 times the reciprocal. So here, this n factorial will cancel out. If I pull this out, I'm left with an n factorial. Those cancel, and I'm left with just n plus 1 in the denominator. Here, base of x, different powers, so those n's cancel, and I have an x on top. So this limit turns into the limit as n goes into infinity of x over n plus 1. Okay. Looking at what happens to n, well, this gets very, very big, right? So the whole thing gets very, very small and goes to 0, which means that my ratio test tells me it's less than 1, and this equals 0. So it is a convergent series when absolute value of x is in between 1, right? So equals 0 means the radius is convergent everywhere, right? The radius of infinity. Therefore, the limit as n goes to infinity of x over n factorial is equal to 0 for every x in R, okay, because this limit gave a 0, oops, which means that we'll talk about this later, but basically this series converges everywhere, right, for every x. So if I look at this series and I compare it to the function here, it should match my function. Okay, coming in and play with decimals a little bit. Let's say we take the function we're just working with, e to the x, okay, and then let's just plug in a couple of approximations, right? I do this in our paper as well, but decimals is always a little bit easier to play with. So for the first one, let's have we'll have y equals. Okay, so if I just have one term, you can see how that's not a very good approximation for my function. But as I start to add terms here, we'll even just put in this factorial x squared. You can see that I have a semi-good approximation. I'm equal at this point, right? If I go 1 over 3 factorial x cubed, look how closely that is to my function, right? So as I continue to just go to infinity, right, I get a better and better approximation, right? Now you can see that we're very close for a little bit longer. Plus 1 over 5 factorial x to the fifth, right? Plus 1 over 6 factorial x to the sixth, right? And if I start to zoom out, you can see, even though we're very far away, you can see how much of a nice approximation that gives. Okay, so if I form us a nice animation, which I will show you in just a second. Okay, so we're back. So I made this, I condensed this a little bit. I wrote the general form. I put a slider here. So if we look at the different step sizes here, right, keep counting by 1, we'll look and see what this looks like as an animation of some sort, right? So here we're going from cubics to fifth dimensions. So as the polynomial gets bigger and bigger and bigger and goes to infinity, I get a better and better representation of my function, right? I'm starting to converge at more places. I have a larger interval of convergence, right? So as you can see, as we keep going, I'm just gonna I'm alternating from even and odd polynomials, and I'm just getting more and more accurate. So what it looks like is that just one side is kind of alternating um, from coming from infinity or coming from negative infinity, right? So here I have a very large value of k, and I'm just slowly creeping on this side to have better and better representations. But over here, it's, it's, it's so large of a value, it's hard to keep up. For the processing power for Desmos here, it's already exactly that value. Okay, so we're using polynomials to approximate a function. As this goes to infinity, it will equal our function. That segues very nicely into this next part. T sub n of x is the nth partial sum of a Taylor series at A. And it's called the nth degree Taylor polynomial of f at A. So what we just saw in Desmos was a single uh, Taylor polynomial, right? Nth degree Taylor polynomial, where we just started to increase the degree. So I think we got what, up to like 50 something, 60, 70 something degree polynomial. So we would have had t to the 75 here for the n, right? So we had a very large polynomial that we just had in our condensed form, but that's what you saw that that continued to grow as the step size was growing, was this nth degree polynomial approximation of our function, right? So again, it's an nth degree polynomial that we use to approximate our function. Notice that for n equals 1, we have the same linearization approximation. Sorry, this would be 0. This would be 1. We have the same linearization approximation that we learned in Calculus 1, right? So in this reader, it would be chapter 5.1. I actually didn't include it in this reader that I'm making at the moment because it's just calculus 2, but at some point I'm going to combine the two, calculus 1 and 2 together, and then when I make my 3, I'll combine that as well. But you could always go back and look at the 5.1 stuff. So in 5.1, we learned linear approximations, right? Where that's where you're first exposed to differentials, the dy and dx terms separately, right? So when I'm looking at n equals 1, right, my function is approximately f of a plus f prime of a times x minus a. Right? So if you go back and look at that, we derived this in a completely different way than we did here. Obviously, we didn't really know too much about series yet. So we came to the same sort of linearization in two different methods, right? So that's, in fact, I think even reference Taylor polynomials in this section, but we don't talk about it obviously because we have no idea what they are. Okay, so the notation for the linear approximation of f, or the linearization of f, is L subscript f of x. So x is still my input variable, and this f is just letting me know that I'm linearizing that function. Okay. So for the nth degree Taylor polynomial, we have the following, right? I'm going to use the subscript I here. A lot of times we would use k, but we're used to I, so we're going to use I. And we'll stop at n because we're going to take the nth degree polynomial. So the notation is still the same. It's just i's instead of n's, right? So this is the ith derivative. This is I factorial, and this is x minus a to the power of I. Right? So when I write this all out, it's the same thing, right? It's f of a, f prime of a over 1 factorial x minus a, so forth until the final term here. Okay. Now, if it's a Maclaurin polynomial, then my a is just 0. And then this isn't x minus a anymore. It's just x and x squared and et cetera, et cetera. And then, of course, the coefficients that go with it. So as with any approximation, right, an approximation does not mean equal. So whenever there's an approximation, there's an error. Okay. The error is the remaining sum that's left over, right? If you think about it, right, even though we're going to infinity, I've added up, I don't know, let's say 50 terms, right? The error is the sum of the rest of the approximation that I would have, or I'm sorry, the rest of the series that I would have. So, so my function is the nth Taylor approximation plus the remainder, right? If I add those two things together, I have the entirety of my function. So let's look at the next theorem. If I have a function that has a Taylor polynomial representation and it's equal to its Taylor polynomial plus the remainder, where Tn is the nth degree polynomial of my function f at a, and the limit as n goes to infinity of the remaining values is equal to 0 for x, for being within the interval of convergence, then f is equal to the sum of its Taylor series on the interval x minus a within R. So this R, this radius of convergence, is not related to this remainder. I mean, they're related, but they're not the same thing. I'm not using one to calculate the other. This value is not the same as this value. They're not the same thing. They are related, but they're not the same thing. Okay. So what this is basically saying is that if the sum of the remaining terms goes to 0, right, then within my interval of convergence, my Taylor series is my Taylor polynomial, I'm sorry, is equal in value to my function. So we kind of saw that where as my polynomial got larger and larger, the interval that it converged onto the function value got larger and larger as well, right? And so when I had something like the linear approximation, I was only equal at one point, that point of intersection. But then once I had a quadratic approximation, when I had n equals 2, um, that quadratic had more area that overlaps with e to the x, right? So that's basically what this is saying, is that if the remainder goes to 0, then my series will be equal in value to my function. Okay. So let's look at the Taylor polynomials for our previous example, where we found the Taylor series for f of x equals e to the x. So we actually just did this on Desmos, but I'm putting it here because I wasn't sure if I was going to go to Desmos or not. But also, if I put it here, that means it's in the course reader. So going through it really quick, you'll be able to see this when you look through the text, right? So here we have our approximation e to the x. This would be the first Taylor approximation, right? So linear functions, linearization of e to the x. You can see it's very close in value around 0, because remember it was a Maclaurin series, so we're centered at 0. And once I move along this line, I get more and more error, right? However, when I have a quadratic approximation, my I'm much closer for much longer. In fact, I'm equal for a longer period of time before I start to diverge away from my series or my function, right? The cubic is even more in line, okay? It's convergent longer. The quadratic, I'm sorry, the fourth degree polynomial is convergent even longer, right? And we saw what this does. It kind of just like creeps along my function, alternating like a string, sort of like wrapping around a stick or a rope or something, right? And so here, if I go far out, t to the 11th, I would be kind of out here. So you can see I'm convergent for much longer than I am for t1, right? So that brings us to Taylor's inequality. If the absolute value of the n plus 1th derivative of my function is bounded, it's less than or equal to some constant value, whenever I'm close to my point of interest, A, okay, so if that's less than some value D, then the remainder, Rn of x, of the Taylor series satisfies the following inequality. So my remainder would then be bounded above and below, actually, right, because this is an inequality or an absolute value, by m divided by n plus 1 factorial times x minus a n plus 1. Now you might be saying, well, this is pretty arbitrary. Where do we get this? There's a lot of math that goes into it that is above the level of this course, so we're not going to discuss that. But in differential equations course, we have a lot of very similar things. Bounding errors and things like that is a big part of that course. So here, what we're doing is we're basically bounding our error. Um, if Yeah, we're bounding our error. Okay. So, and again, this is when I'm close within a distance of d from my point of interest, right? So let's look at an example. So show that e to the x, which we've been working with already, is equal to the sum of its Taylor series that is centered at a equals 0. So basically saying, show that e to the x is equal to its Maclaurin series. Okay. We know that the Taylor series centered at a equals 0 is called the Maclaurin series that we derived in the previous example. Okay. So here we have f, the n plus 1th derivative is always going to equal e to the x, right? All of the derivatives of e to the x is e to the x. So this is true for every n. So I need e to the x, the absolute value of this, to be less than or equal to m, for x being less than or equal to some value d. So I need a bound for e to the x, right? And we see already what e to the x is. It goes on forever, right? It increases. Um, so well, we'll have to be a little bit trickier. So now you might be saying, why ETX? We have to satisfy the conditions first before we talk about the inequality. So the condition is that the n plus 1th derivative is bounded. Well, while I am close in value to where I'm centered at, in this case, 0, right? So when I'm close to 0, um, within a distance of d, of x equals 0, I should say, um, the nth derivative, e to the x in this case, has to be bounded by some value, right? If that's true, if this is true, then my remainder, right, is bounded by that same value divided by n factorial x minus a n plus 1 power. Okay. So letting m equal e to the d, since the absolute value of x is less than or equal to d, right? So my x value, this value here, the largest value I'm allowing it to be is d. We know e to the x continues to grow. So if e to the x is never larger than e to the d, I'm going to let x be the largest value that I can, which is d. So m is this e to the d value. Again, since x has the largest value of d. Okay. So the n plus 1th derivative of e to the x is just e to the x, which is less than or equal to e to the d, since d is the largest value x is allowed to take. on and e to the x is increasing, which is equal to m, that means that this thing is less than or equal to m. Okay? So since that is true, Taylor's inequality gives us that the remainder of my Taylor series is less than or equal to this bound, e to the d, over n plus 1 factorial times x to the n plus 1 power, right? So again, this value is really going to be determined by what the remainder is, right? If I'm taking a 10th degree Taylor approximation, well, then n is 10, and then I can plug in values here. E to the d, although I don't have a value for d, I know that I can bound it, though, by x to the 11th degree here, and then 11 factorial, right? Because it's n plus 1. So if I take the limit of both sides of these things, okay, the limit of Rn is less than, this is a constant, so I can pull it out, this e to the d, times the limit of what's remaining, x to the n plus 1 over n plus 1 factorial. Okay. I know that this is going to go to 0 because this is going to grow faster than this is going to grow, okay, which means that my limit then has to be less than or equal to 0. And since it's absolute value, that means it has to equal 0. Okay. Therefore, the limit of the remainder of the nth Taylor approximation is 0. Therefore, e to the x is equal to the Maclaurin series. Because, remember my initial condition, right? If the limit of the remainder goes to 0 as n goes to infinity, then f of x is the Taylor approximation plus its remainder. Okay? Then the sum of the Taylor series on the interval. So, our approximations were equal uh, as long as we were taking the n polynomial. Okay, therefore e to the x is equal to its Maclaurin series. So let's look at some important Maclaurin series. So we dealt with e to the x. We've also talked about 1 over 1 minus x. That's how we were introduced into power series, and we, manipulated that a little bit. But 1 over 1 to the x isn't super common function. Like, yeah, we can use that to find other functions, but it's not something we deal with a lot. E to the x comes up pretty often, especially when you get into differential equations. You actually start to do series solutions to these things. So you actually use um, this e to the x value all over the place, right? There's a lot of series notation that happens in diffq. Um, Here we go. So this one we already knew. So there's a lot of other functions, right? What about sine? What about cosine? What about tangent? What about cosh? What about right? There's all these other things that are interesting to us that we use that we have not discussed yet. The first one that we studied was this 1 over 1 minus x, which is the basic power series with a coefficient of 1. For the next one, here we go. So the radius of convergence here is r equals 1. We saw that previously. For e to the x, we already know what the series is, and we know its radius of convergence is infinity, right? It converges into the whole function, right? Here, this approximation would only approximate over um, a radius of 1, right? So from -1 to 1 for this function centered at 0, right? Whereas this one converges everywhere. It should make sense because if we're centered at 0 and we start to move towards 1, we get into an undefined issue here, right? So it makes sense that this can't be everywhere. All right. For sine, our series is -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. We've actually seen this in previous videos, but we didn't tell you that it was a sine. So we actually did see this previously. What does this look like in general? It'll be x minus 1 over 3 factorial, x cubed, plus 1 over 5 factorial, x to the fifth. So it's all the odd powers, right? It's just all the odd terms. So power of 1, 3, 5, 7, 9, 11, etc. And we're alternating in sign, okay? This should make sense to you why sine is an odd function, right? We only have the odd powers, right? So this is an odd polynomial. So it makes sense why sine is an odd function. This converges for infinity, okay, over the whole function. And cosine, we know, is an even function, and it has the exact same form, but instead of 2n plus 1, it's 2n everywhere, top and bottom. So its general form is all of the even terms, the zero term, the squared term, the fourth term, sixth power term, eighth power term, etc. And it also alternates in sign. Okay, sine is odd, cosine is even. To be honest with you, the only reason I remember that sine and cosine is even or odd is because of the forms of their Maclaurin series. Okay, so again, this converges for all of R as well. The tan inverse, this is alternating as well. This is just like sine, except not with a factorial. Okay, that's really the difference. This is just going to count by the odd terms instead of having them factorialized. So x minus 1/3 x cubed, 1/5 x to the fifth, etc., etc. Okay, and so this is convergent with, over a radius of 1. Natural log of 1 plus x is -1 to the n minus 1 power, x to the n over n. Okay. We saw this a little bit when we were dealing with this. We had a natural log of a function, although it was different. It was 1 plus x over 1 minus x, I believe. But we separated into two series and kind of seeing what that looked like. Term by term is very similar to this tan function, except that it counts by 1 each time. So x, and then half, and then threes, and then fours, not just the odds. Okay. This has a radius of convergence of 1 as well. Then we have 1 plus x to the k. This is actually a very important one. We'll talk about this quite a bit later. And it's given by the sum of k choose n, x to the nth. So this has to do with permutations and combinations, really combinations. And it's basically a binomial form, right? Binomial expansion form. Talked about this a lot in the pre-calculus. I know I referenced that a lot, but we have what's called Pascal's triangle, which is super, super, super useful for things like this. I suggest you kind of check that out. It's towards the end of the pre-calculus stuff. I don't remember what it is actually. I think it's actually in the series section. I think we discussed this as well. All right, but this binomial term, this n choose k, super, super important, right? Or k choose n, I believe here. Anyways, so this is important whenever we have a binomial that we need to expand to a power of k, right? So k choose n or n choose k, I can't remember the way that we say it, although it's technically pretty much the same thing. X to the nth power, so I have 1 k is given by this, right? 1 over 2 factorial k times k minus 1 is given by this term, this n choose k. 1 over 3 factorial k times k minus 1 times k minus 2. For the next one, it would be 1 over 4 factorial times k minus 1, k minus 2, k minus 3, etc., etc. This is convergent over a radius of 1. Okay, and so then that brings us to the binomial series. We'll talk about this a little bit more, but that pre-calculus um, section on the binomial is will be super, super helpful to look at now before you come here. Although it's up to you, maybe you'll get through this without having to look at that, right? Or maybe you're familiar with it, but I don't go over Pascal's triangle here, but I do in the other series, and it's a good discussion as well, right? So the binomial series. If k is an integer, a real number, not an integer, I'm sorry, a real number, and x has an interval of 1, right? Less than 1, so in between -1 and 1, then this binomial expansion here, given by the sum of n choose k x to the n, is equal to this series that we just discussed, right? This is called the binomial series, right? And it has binomial coefficients, this n choose k that we have here. So n choose k is given as a formula as the top number factorial, the difference between these two numbers factorial, k being the larger and n being the smaller. It doesn't really matter. You can go the opposite way and it works the same way. And then the bottom number factorial, right? So top number on top, bottom number is the difference between the two factorial, and then the bottom number and factorial. So if we expand this, we get k times k minus 1 times k minus 2 times k minus 3, etc., etc. This is an intermediary term where we're at k minus n plus 1, and then uh, we're going to have k minus n minus 1, and so forth till we get down to 2 and 1. We do not include 0. Because if there was a 0 on top, obviously everything goes to 0. We've already discussed this, but don't forget that. On the bottom, I have k minus n factorial, which matches up right here. K minus n, k minus n minus 1, etc., down to 2 minus 1. I also have n factorial. So I'll put the n factorial over here, and I'll line up my k minus n factorial over here with everything that it cancels with. Okay. So then what I'm left with is just this stuff, right? K minus 1, k minus 2, down to k minus 1 more than n, right? Over n factorial. So let's look at some examples. Okay. Number one, let's find the Taylor series for f of x equals 1 over x, centered at a equals -3. Okay. So this is not a Maclaurin series. This is a Taylor series, so it's a little bit more convoluted, although it's not terrible. Right? We want to also find the radius of convergence. So our function is 1 over x. F of x evaluated at -3 is -1/3. We need to find some derivatives and evaluate them at -3. So the first derivative is -1 over x squared. When I plug in -3 to that, I get 1 over 9. Okay, -1 over 9. The second derivative is 1 times 2 over x cubed. Okay, plug in -3 to that, I get -2 over 27. Okay, and so as we continue, right, we have -1 times 2 times 3 over x to the fourth. Plug in -3, I got -6 over 81. Okay. Therefore, 1 over x has the series, the Taylor series, evaluated at -3 of -1 over 3 minus 1 over 3 squared, 1 factorial, x plus 3, because remember it's minus, so x minus a -3. Here I have 2 over 3 cubed, 2 factorial, x plus 3 squared, then 6 over 3, right? That's this one, 6. This is, I plugged in 3 here, so that's 3 to the fourth power over 3 factorial, x plus 3 to the third. So then now let's simplify these coefficients. So instead of writing the -6 over 81 and the 1, well, 1/3 can stay, but this 1 over 9 and the 2 over 27, notice I'm writing them in simplified forms with the factorials that's showing up in the powers of x, because it'll help me to form the generalized form. So when I start to simplify this one, right, when I flip the reciprocal of this, it's just 1 over 3 squared. Then I have a 3 cubed, a 3 to the fourth, and notice that that factorial starts to multiply once I multiply by its reciprocal. Okay, so it's very clear to see what the pattern is in the denominator. That's the reason why I didn't actually multiply anything out, because it actually hurts me here, right? So keeping it in its generalized form as I was doing the math allows me to get a better idea of what was happening. Here in the numerator, I don't know. So I had one, and then 2, and then 3. So maybe I'm doubling things. Um, I don't know. The pattern isn't super clear exactly what's going on, but you can see that there is factorials going on. So 1 factorial, 2 factorial, 3 factorial. That's why I left this one in a generalized form, because that 6 over 81 is really 3 factorial over 3 to the 4th. So I know what this is, right? So those actually cancel, right? Because this is 1 factorial over 1 factorial, 2 factorial over 2 factorial, 3 factorial over 3 factorial. So I'm left with is just the powers of 3 increasing by 1. And then I have x minus my a value, or x plus 3 in this case, and then the powers on top. So it's very easy then for me to write the generalized form for this Taylor series expansion, right? Centered at x equals -3. Now, if I didn't keep this in a generalized form, I probably would not have been able to figure out what the hell the coefficients look like as a generalized term. So just a word of advice to the more things you keep in general here, um, the easier it is. So if you're used to using your calculator and expanding everything, not going to be super helpful for writing a generalized term. Okay. Now, if I look at what this looks like using the ratio test as far as convergence, right? Because it'd be nice to know what the radius of convergence is. I take everything and I add +1 for all the n's, and I take it and I multiply it by this reciprocal, and things are going to cancel, right? This is n plus 1, n plus 2, so I have 1, 3 on the bottom. This is x plus 3, this is x plus 3, there's n plus 1 here and an n here, so I'll be left with x plus 3 on top and a 3 in the denominator. And I need this to be less than 1 in order for it to converge. So that will help me form my radius, right? So now I can multiply both sides by 3, okay? And then when I form my inequality that I want to solve to find the actual interval, it will give me, I'll be convergent from negative uh, 6 to positive 6, right? No, from 0 to 6. And so I would then have to look at the end results, right? However, I'm really just interested in the radius, right? That's what it looked for. It said find the radius of convergence, not the interval. So it's nice to know how to find the interval when I need to, but all I needed was the radius. So that radius here is 3, and it's centered at -3. Look at the next example. So find the Maclaurin series for f of x equals x cosine 1/2 x squared. So definitely would have been very, very hard to try to find this power series any other way. So now that we have a generalized form for cosine, we'll do what we did when we in the last section. We just plug stuff in and we multiply stuff, right? So we can figure out by using our base of cosine already. So remember, cosine is even, right? So it has 2n factorial on the bottom and x to the 2n on top. This is its generalized form. So to cosine, we will be manipulating it in a way that we find the Maclaurin series for what we need. Okay, so let's come back here. All right, so cosine of x is the sum from n equals 0 to infinity, alternating in signs, x to the 2n and 2n factorial. So what we need is plug in this 1/2 x squared into that, right? So here you see that when we do this, this is going to turn to x to the 4n. We can pull out this whole 1/2 or just the 2 and move it to the bottom with this 2n if I want to. We're just going to go ahead and separate it. Okay. So this -1 to the n, the 1/2 to the 2n, x is now to the 4n, and I have my 2 factorial. Okay. So I have the cosine part. There's really nothing here for me to simplify from here too much. I could just apply this 2n straight here instead. Um, I also need to multiply this times x. Okay. So x cosine 1/2 x squared. It's going to have a generalized form of, instead of 4n, I moved one more in, so it'll be +1. I do not need to write out a whole bunch of terms here. Whenever we have the generalized form, that's really what we prefer because then we can do analysis on it, right? If I wanted to integrate this function, I could integrate this term by term, I could integrate the entire sum as well. So a lot of times we really just want to play with the sum, the generalized formula, okay? Not a bunch of terms, right? So this would be my answer, right? If I wanted to, just went ahead and took this 2 and we applied that power of 2n to it, so that's why we have this 4n. So this is probably the most condensed formula we could have for this, so that's what we would leave it as. So for the next example, use series to approximate the integral from 0 to 1 of sine of x to the 4th power with respect to x up to 4 decimal places. So similar to what we had in the last series, we can use a series, and we really just want to add stuff up until it starts to um, stabilize at the 4th decimal place. That's one way to go about it. Another way is to start to use this remainder theorem, right? So we have sine of x is the sum from 0 to infinity, -1 to the n. Here we have all the odd stuff, right? We have this factorial and this odd power for x. We need to get this x to the 4th term, so we're going to replace all of our x's with x to the 4th. So right here, so I'll have an 8n plus 1 in the numerator, and this 2n plus 1 factorial. And so for if I look at this term by term, I have x to the fourth minus 1 over 3 factorial, x to the 12th, right? When I plug in 1 here, I get 8 plus 4, plus 1 over 5 factorial, x to the 20, and so forth, right? So I don't have to integrate term by term. If I want to just find the integral of sine of x to the fourth, I can integrate its general form, okay? So remember what I was saying, I don't have to do term by term. Just, sometimes it's nice to see what the terms look like. So here, if I integrate the entire function, um, I multiply by the reciprocal of this power, right, times what I have already, and this power increases by 1. So this is the generalized form, okay? So if I want to go from 0 to 1, I can uh, look at what happens when I plug in 0 and when I plug in 1. So I integrated it, so I plug in 1 to look at, see if I can find out what the sum is here, and subtract that from what I think the sum is here. So I have this constant from integration, this alternating series that I had. Remember, I plugged in 1 here, so I really am just looking at this series term. Hopefully I could find its actual sum. Here, when I plug in 0, the whole thing goes to 0, and I just have this constant. But notice what happens with these constants. I have c minus c. So those constants actually go away, and I just have to focus on this sum. So if I could find the sum, this will give me the sum uh, from 0 to 1 for this function. So if I look at each term and try to find the sum for this, that'll be helpful. Okay, so here we have 1. This gives me 5 when I plug in 0. 0 here just gives me 1 factorial. Okay. For the next one, when I plug in 2, I'm going to get, I'm sorry, when I plug in 1, get 13. Here, I get 3 factorial, right? 21, 5 factorial, minus 29 times 7 factorial, plus 37 times 9 factorial, et cetera, right? Plus and minus, plus and minus. And so this is 0.2. So again, I just need, this is an alternating series, right? Once I get to a term that is within 4 decimal places, the remaining amount that I have of this is not going to offer anything significant to change that 4th decimal place. Okay. So this first term is really just 1 over 5, which is 0.2. This is 0.01. Okay. This is basically 0.004. Okay, if I kind of just round off. So here I stabilize at 3. Okay. The next value of this term is 1, 2, 3, 4, 5 zeros, and then 7. So it's stable to 5 places. So if I add up these first 4 terms, nothing else after that can affect the first 4 decimal places, right? So I need to add up more than this because this is 004. If this was 001, then I could stop here, right? But it's not accurate enough, so I need to include this 4th term, right? So after the 3rd term, no significant values are added based on the tolerance I'm specifying. So I just add up these first 4 terms, okay, which is 0.1875763, right? The true value is 0.1875695 and some change. So you can see it's very clear here that we're stable to the first 4 decimal places, and then after that, we start to have variation. Okay? So we're correct 4 decimal places. So for part D, let's find the Maclaurin series for y equals x divided by sine of x. Okay, so we can do this term by term by looking at the derivatives and evaluating them at 0, but we know what sine of x looks like, so instead we can just divide polynomials. Okay, I can take this x and I can divide it by the series for sine of x, right? So we know that this is really one long polynomial. Um, So we'll do that division instead of the standard way. We can do it the standard way, but we can also do it by using long division, especially since as I find more and more derivatives of this, continuing to use the quotient rule, I'm going to get really, really hard things to evaluate, right? This is going to get, it's going to be really hard to find high derivatives of this thing using quotient rule repeatedly, right? So we're going to do long division. So if you don't remember how to do long division on polynomials, you can look in my review in Calculus 1. But quickly, it's really just like regular log division. So this is my leading term. This is my leading term. This is being divided by this. So what times x will give me just a regular x? The value is 1. Okay. So I take 1 times this polynomial, right? The series here, and I subtract it from what I have. So I'm going to subtract x minus 1 over 3 factorial, x cubed plus 1 over 5 factorial, x to the fifth, etc., etc. I don't have to write everything, just enough for me to get a general idea what's going to happen here. I do the subtraction. Really, this is the only thing that goes away. Remember, there's zeros here, right? So I'm going to have 0 minus a negative of this, so it'll just be this term positive, this term negative, this term positive, right? So they're just going to change signs on me. So now I'm looking at this and I'm saying to myself, what do I multiply times x in order to get 1 over 3 factorial x cubed? Well, I already have an x cubed, or I already have an x, so I just need an x squared term. I don't have anything multiplied times it, so I need a 1 over 3 factorial. So here I will have 1 over 3 factorial x squared, right? So I multiply this term times my entire polynomial. So the first term is 1 over 3 factorial x cubed, and I multiply this times this. I have 1 over 3 factorial, x to the fifth, right? X squared and x cubed. For the next term, that's the 1 over 3 factorial, 5 factorial, x5 and x squared gives me the x to the seventh power, and so forth. Now I do my subtraction, okay? This goes away, and this is what I'm left with here. It's a fraction of fractions. I had to make a common denominator. Same thing here, had to make a common denominator. It's getting a little wild, so I'll just include this next term because it's really easy, right? I need 4 x's in order to get to the fifth. I have no idea what number this is, but that's what I need to multiply it in order to get it to subtract. So here, I just switch it around so that the 5 is in front, okay? I multiply this times that, I would get this first term, subtract it times everything, right? Which I'm not going to do. I have the first 3 terms. So x over sine over x, this is the first 3 terms. Again, you see I try to keep everything generalized to see if I could find a pattern. I can't. I have no idea what the hell's going on here. So I'm just going to give the first 3 terms instead. Okay. Ideally, first 4 terms would be great, but that's going to be a lot of work for this next one. And we have a good idea of what's happening here. Okay. So then that would be the Maclaurin series for x divided by sine over x. Next, let's consider the Maclaurin series. So here we had a divide. Okay. Here I'm squaring something. I don't square term by term. I take this series for sine of x and I multiply it times itself. Same thing for cosine. I take its series and I multiply it times itself. So sine squared is going to be the series times itself. I don't just double everything. It doesn't work that way. In fact, I can't even just say, oh, it's x to the 2n plus 1 times x to the 2n plus. It doesn't work that way either. I can't just multiply these factorials times each other. That's not how the multiplication works through a series. So what I have to do is I need to write out term by term. Okay. And then I'm going to multiply each uh, each one to find the term by term form for sine squared of x. So first thing I'm looking for is what is the lowest power possible by multiplying these two things. Well, lowest power, lowest power. If I multiply x times x, I get an x squared. I look and I say, how else can I multiply these terms times these terms to get an x squared term? And there's no way, right? The next lowest term is x to the fourth. So my first value is x squared, and that comes from the first term times the first term. The next lowest possible value is x times x cubed, which would give me x to the fourth. The other way to get x to the fourth is if I multiply this x cubed term times the first term. So I'll have x times this, and I'll add it to x times this term. There's no other way to get to x to the fourth power. So what does that look like? That's x to the fourth, and I have negative 3 factorial. When I multiply x times this one, I have a negative 1 over 3 factorial x to the fourth. So then I do the next thing. What's the next lowest power possible? Well, x times the fifth power will give me x to the sixth. So I need to multiply that together. And I say, well, I was going to get x to the sixth. Well, this is already seventh and this is already seventh, so anything past that isn't going to work. So I can go x times this term. I can go this third term, the second term times the second term, the one with the 3 power. And this fifth power times the first power will also give me a sixth power. So what does that look like? I have 1 over 5 factorial, x to the sixth. I have negative 3 factorial times another negative 3 factorial, so that'll be positive. So 1 3 factorial times another 1 over 3 factorial. And then this first term and this first term will give me another 1 over 5 factorial. So those are all the x to the sixes. The next lowest possible would be x to the 8. And what are other ways to do that? This 3 and this 5, this 5 and this 3, and this 7 and this one. But I don't need to go that far, right? I have 3 terms. I have a general idea of what's happening here. And so if I do the same thing for cosine, the same thing. I'm multiplying these things out. So I write them out term by term. Same thing. 1 times 1 is the lowest thing I can get. So that first term is 1. You see here it starts on the next line because this is too long to keep on one line. The next lowest thing I have is an x squared. So this first and this second term give me an x squared, and this first and this second term give me an x squared. So for the first one, I have a negative 2 factorial, and from 1 in this second term, I have another negative 2 factorial. That's all the x squares. The next lowest thing I can do is an x to the fourth. So I have a 1 over 4 factorial. These two can multiply, so I have a 2 factorial, 2 factorial. They're both negative, so it's positive. And then I have this 1 and this 4. So that's what it looks like for the fourth term. For the sixth term, we can just write everything out. So 1 in the 6, 4 in the 2, this 4 and this 2, and this 1 and this 6. So all of those products being added together times x to the 6. Very clear to see here that this is negative, this is positive, this is negative. So this is going to be alternating in sign. Positive, negative, positives. Everything on the next one will be negative. So this is also alternating in sign still. Okay. Notice that my sine squared went from being all odd powers to now being all even powers, 2, 4, 6, etc. Cosine was all even powers, and then cosine squared is all even powers also, 2, 4, 6. The next one would be 8. So when I add these things together, sine squared plus the cosine squared, I'm going to take this result and I'm going to add it to this result. Okay. Notice I haven't actually really added anything together yet. I just have the general form from the multiplication I did. So here's just the 1. There's no 1 over here. Here I have just a 2. So I got to actually figure out what this is, right? So I have 1 from cosine squared. I have two x2 terms to add together. So this is 1, right, from x sine squared, because notice I'm going sine squared plus cosine squared. So I have 1 here. And when I add these together, I have 2 factorials that are negative. Okay. For my next term, I have 2 negative 3 factorials, and I'm going to add that to, I have 2 of these 4 factorials and 1 of these 2 factorial 2 factorials. Right? And I do the next thing with the sixth term. I'll take all the stuff in here. I have 2 5 factorials and a 3 factorial times 3 factorial. Here I'm subtracting from that a 6 and a 6 factorial, so there's 2 of them. And then these, they're opposite in order, but they're exactly the same value, so there's 2 of them also. Okay. Now I haven't actually multiplied stuff out, okay, and I will continue to do this. So if I start to simplify stuff here, right, this is 1, okay. Here I'm going to make a common denominator. So I need this to be 2 factorial over 2 factorial. So that's why this is 2 factorial minus 2 over 2 for x squares. Here I need a common denominator. So there's a 3 factorial, 4 factorial, and 2 factorial, 2 factorial. So the biggest one is 4, right? I'm not going to multiply 3 and 4 together to get 12 factorial. It doesn't work that way. Remember, this is 3 times 2 times 1. This is 4 times 3 times 2 times 1, etc., etc. So between this term and this term, the only thing that's missing is the power of 4, right? So this I would multiply top and bottom times 4, and then the bottom would turn into a 4 factorial, and then I can add these together. Okay, here I have 4, and what I'm missing is 3 and 2 in order to have 4 factorial. So that's what I do. Here, I multiply this top and bottom by 4, so that's why I have 2 times 4. The middle term, I don't have to add anything. The last term here, I need to include a 3 and a 2. So 3 times 2 times 1 is 3 factorial, so it's just easier to write 3 factorial here. So now I have a common denominator, and I have my numerator. Same thing here. The highest factorial is 6. So this is missing a 6. This is 3 times 2. Um, this is 3 times 2. So I need a 6. So 3 times 2 is actually 6. So the only thing that's missing from here is a 5 and a 4, actually. Okay. The middle gets a 4 and a 5. This one I'm missing a 6. Oops. Okay. I'm missing a 6 here. So the top gets the 6. Okay. Here, this is 3 factorial times 6, right? 3 times 2. So it's missing is 4 and 5. So I use 4 and 5 here. The middle term is 6 factorial, so I don't have to add anything, multiply by anything. Here, I have 4 factorial. I don't have a 5 anywhere. And 3 times 2 is 6, so I'm just missing a 3 and a 5 on this numerator. Okay, 4 factorial. The reason we have a 5 and a 6 here is because I canceled these 2's. That's why there's a 1 here. So I cancel these 2's, so then what I'm missing from this 4 is the 5 and the 6, right? So if I cancel the 2's out, in order to get this to a 6 factorial, I need 5 and 6. So that's why you have 1, 5, and 6 here. So if you actually do the math, 2 factorial is just 2. 2 minus 2 is 0, right? This is 8, right? This is 2 plus 6, so positive 8, so that's 0. This is 30. This is 20, so there's a negative 10 left over. And this is 8 and a negative 2. So those things, I'm sorry, 12 and a negative 2, which gives me 10. So positive 10 and a negative 10 give me 0. So everything is going to cancel out, and I'm going to be left with 1, which should not be a surprise because this is a trig identity, right? Sine squared x plus cosine squared x is equal to 1. So we just verified this by using series, right? F, our last example. Find the sum from 0 to infinity of this alternating series. Here we have pi to the 2n over 6 to the 2n times 2n factorial. So let's look at something that maybe looks like this, okay? Because we have a lot of constants in here. If you notice, there's no x. All of the things we've been doing here have to do with series, right? And so the series of a function. So this was in the binomial, a list of functions. So we had a lot of 2 to the n's, not with the plus ones, just 2 to the n. So cosine has 2 to the n's and factorials, and the binomial series does not. Okay, so we'll probably have to use the cosine, standard cosine form for that. So here you see 2n and a 2n factorial. That's kind of a giveaway here. There's no x's, so it looks like there's another 2n. So it looks like we are actually plugging something into cosine. So let's kind of group these 2n stuff um, outside together, right? So pi and 6, the whole thing to the 2n. Well, now I have something to the power of 2n over 2n factorial. This looks a lot more like cosine. And it's just if I were to plug in pi over 6 into cosine. So instead of looking at all these values and trying to add them up, right, I can just plug in pi over 6 into cosine, which is root 3 over 2. Okay. So try not to get hyper focused on trying to expand things and look at everything. Sometimes you got to step back and just play with the sequence in general. Okay. So I hope you guys like this. We only have one more video left for Calculus 2. The next section, the last one, is going to be on Fourier series. So just like this was a series named after a person, this is another series named after Joseph Fourier. For the next section, very, very important, used all over the place in engineering physics and especially higher level mathematics. So see you guys in a minute.